Greetings to you on the channel. Before we begin, I'd like to ask you to support the project by subscribing to the Telegram and YouTube channels, clicking the bell to receive all notifications, liking if you found it interesting, and writing comments. You can also follow the links in the video description to the articles and read them. This will greatly help the channel.
You ever get that feeling that our gadgets are packed with more and more amazing features, but sometimes the wireless connection just doesn't feel right? Well, today we're going to pull back the curtain on a hidden battle that's happening inside pretty much all of our tech. It's a fundamental physics problem, and we are about to dive right in.
So, picture this. You've just unboxed the latest, greatest gadget. It's sleek, it's powerful, and it is jam-packed with antennas for 5G, for Wi-Fi, Bluetooth, you name it. But then you run a speed test, and the performance is a staggering 30% worse than it's supposed to be. So, what in the world is going on? Yeah, a 30% drop. That is not a small number. That's the difference between streaming a movie in beautiful 4K and staring at that dreaded buffering wheel. And this isn't some software bug. Nope, this is a physics problem, and it's one that engineers are fighting every single day.
The culprit has a name, and it's called mutual coupling. It's what happens when we cram all these antennas so close together that they just stop acting like individuals and start, well, getting in each other's way.
You know, you can think of your antennas like neighbors living in an apartment building. When they're spread out, they can each blast their music without bothering anyone. But as you pack them into a smaller and smaller space, like, say, inside a smartphone, they start sharing walls. And now one antenna's music, its electromagnetic field, starts bleeding right through the walls and messing with its neighbors.
So how does this energy leak actually happen? Well, there are three main ways. First, you've got simple free space radiation. The signal literally just reaches out and pokes its neighbor. Second, you get these unwanted surface currents, where energy flows along shared metal parts, like the device's chassis. And third, energy can travel as surface waves right through the circuit board itself. It's basically a three-prong attack on your device's performance.
And the cost of all this interference? It isn't just theoretical. It shows up in very real, very measurable ways that directly tank your user experience.
Okay, so check out how this damage just cascades. First, the input impedance gets all messed up. Think of it like a clogged fuel line. The antenna just can't accept power efficiently. Then, that causes the radiation patterns to get distorted, so the signal isn't going where it's supposed to. All of this narrows the entire data highway, and that huge benefit of modern tech, diversity gain, where you use multiple pads for a stable signal, it gets completely strangled.
And these numbers right here show you exactly what a difference good design makes. With poor isolation between antennas, that unwanted signal power is way too high. But by improving that isolation, engineers can absolutely slash the interference. And this isn't just some tiny tweak. For a product designer, this is literally the difference between passing certification and failing completely.
So here's the bottom line. There is a hard limit. For the kind of high-speed, high-quality data we all expect for things like video calls and gaming, those walls between the antennas have to provide at least negative 15 decibels of isolation. Anything less than that, and the whole system just starts to fall apart.
Okay, so if the antennas are shouting at each other, how do we get them to quiet down? Well, fortunately, engineers have a whole toolkit full of really clever solutions to fight back. And it all starts with changing the physical design.
The first line of defense is physical. Engineers can build these things called decoupling networks that brilliantly create an opposite signal to cancel out the interference. They can actually modify the ground plane itself, cutting tiny slots or adding stubs that act like roadblocks for those unwanted currents. They can even use advanced metasurfaces or resonators that basically trap and get rid of the interfering energy before it can cause any trouble.
And these techniques, they are incredibly effective. This quote from a real-world project shows a massive jump in isolation and a near-total elimination of that unwanted correlation. I mean, that is an engineer achieving a huge victory, proving that with smart design you really can tame this beast.
But here's the twist. What happens when you can't change the hardware? Maybe the device is already being manufactured, or maybe there's just no physical space left for these extra components. Is that performance just lost forever?
This leads to a really fascinating question. Can you use software to fix a fundamental hardware problem? Well, the answer, as it turns out, is a resounding yes.
See, if you can't physically stop the antennas from talking to each other, you can teach the system to understand their garbled conversation. Algorithms can adaptively tune the antennas on the fly, they can use digital processing to mathematically subtract the interference, or, and this is my favorite, they can even design the wireless beams in a way that cleverly works with the coupling instead of fighting against it. How cool is that?
Now, this battle is far from over. In fact, as our technology keeps getting smaller, faster, and more connected, the fight against mutual coupling is only going to get more intense.
So how do engineers win? Here's a cheat sheet from an expert in the field. And it really boils down to this. Plan ahead, simulate everything, build decoupling in from the very start, and always measure the real hardware. And most of the time, the best solution isn't one single trick, but a hybrid approach that combines a few of these techniques.
And they're going to need every tool they can get. Today, the challenge is dense 5G arrays. But tomorrow, with 6G systems running at terahertz frequencies, the wavelengths will be microscopic, making this coupling problem even more severe. And way out in the future, with concepts like holographic MIMO, the antennas will be so dense that coupling becomes the main effect to deal with, not just some annoying little problem.
To meet a challenge like that, the tools themselves have to evolve. We're moving away from manual design and toward AI-driven optimization, where machine learning could discover solutions humans might never even think of. And we're looking at advanced tunable materials that can actually change their properties on the fly to suppress interference in real time.
And that brings us to what I think is the perfect summary of this whole engineering challenge. The goal isn't always to silence the antennas completely. In our super dense, compact devices, that's pretty much impossible. The real goal is to manage the conversation, to turn a performance-killing shout into a manageable whisper.
Which leaves us with one final thought. We've just seen how we literally have to teach our own creations how to behave properly when they're in close quarters. As our technology continues to shrink and connect every single part of our lives, what other fundamental lessons in physics and cooperation are we going to have to teach it next?